Chapter 8, The Nucleus. The Thomson Model of the atom. Atoms are positively charged lumps of material with electron embedded in them. The Thomson model of the atom has the electrons represented here as blue positive, blue negative structures embedded within a positive structure. That's the Thomson model of the atom. The Rutherford experiment, Ernest Rutherford bombarded nuclei with alpha particles, which are strip helium nuclei. If the Thomson model was correct, the alpha particles would not be significantly deflected. However, the alpha particles were deflected, in some cases through large angles. The principle of Rutherford experiment. So here we have a source of alpha particles with a small slit in lead. And the few alpha particles get through, they impinge on the gold metal foil, and then you can see luminous spots on the screen, indicating that the screen has been impacted with the alpha particles. Another illustration. Let's see.
In Rutherford scattering, a beam of alpha particles, pictured in red, is ejected towards a gold foil target, surrounded by a circular blue detecting screen. Alpha particles scattered by the gold can be seen as spots of light hitting the detector at different locations. As we zoom into the gold foil, we can see in this magnified view that occasionally an alpha particle will collide with a gold nucleus pictured as black dots and get scattered. This experiment established that atoms consist of a very small central core of heavy protons and neutrons, surrounded by very light electrons. Thus, most of an atom's volume is empty space.
So the Rutherford model of the atom is largely empty space. Positive charge is concentrated at the nucleus. The negatively charged electrons surround the nucleus at a distance. Here is another rendition then. Strip helium nuclei coming in from the left, and you can see them being scattered on the right. Nuclei are made up of two types of nucleons. The protons, positively charged, about 1,836 times the mass of an electron. And the neutrons, that is about 1,839 times the mass of an electron. Now the notion of helium, hydrogen, lithium, and beryllium. The Rutherford model of the hydrogen atom, the nucleus is there within one electron. Helium there with 2 protons and 2 electrons. There are some neutrons also. Same with lithium with 3 protons and 3 electrons, 2 in the nearest shell and 1 in the outer shell, and beryllium, and so it goes on and on. Of the over 100 known elements at room temperature, 10 are gases, 2 are liquids, the rest are solid. More than 88 are solids. Isotopes. Elements are labeled by their charge. 2 atoms of a given element can have a different number of neutrons, and therefore they will have a different mass number, and we call these then isotopes. An example, ordinary hydrogen has only a proton and 1 electron, no neutron. Deuterium has 1 proton, 1 neutron, and 1 electron, of course, and tritium has 2 neutrons, 1 proton and 1 electron. Both deuterium and tritium are radioactive isotopes. The nuclide symbol is this structure, an X, and a superscript A, and a subscript Z. The X is the chemical symbol of the element. The Z is the atomic number of the element, the number of protons, and capital A, the mass number, the number of protons and neutrons added. An example, this then becomes chlorine 3517, and chlorine 3517 has 17 protons. It has 8 neutrons plus 7 protons give 35, so that's why it is Cl3517. Radioactive decay. Unstable nuclei decay by emitting particles. The first kind of particle that can be emitted is the alpha particle. It's a nuclei of a helium atom that does not have its electrons, so we call it a strip helium atom. And the beta particle is merely an electron, and the gamma ray, energetic photons. An example then, if you have what is thought a radioactive source here, with all 3 kinds of radioactive particles present, you will find that alpha particles get deflected to the left, beta particles that are charged negatively get deflected to the right, but gamma rays are not deflected at all. And once again, the gamma ray is the most penetrating of the 3. Gamma rays will go through cardboard and then on through aluminum and even through lead. But you will see that aluminum will stop beta particles and cardboard simply will stop alpha particles. Why decays occurs? Alpha decay occurs if nuclear forces are insufficient to hold the nuclear particles together. Beta decay occurs if the ratio of the neutrons to the protons is not large enough, and gamma decay occurs if the nucleus has excess energy. The 5 kinds of radioactive decay are listed here, and briefly they are gamma ray decay, alpha decay, beta decay, electron capture, and positron emission. An example of a nuclear decay. Find the symbol of the nuclide into which the uranium isotope U-232 is transformed when it undergoes an alpha decay. So it must end up with an alpha particle here, and with 2 protons and 4 sum of protons and neutrons. So it ends up as being a thorium 228. I'm sorry. The half-life. The half-life of a radionuclide is the period of time for half of its initially present amount to decay. An illustration is here.
The number of remaining 13N nuclei declines with time. 13N is an unstable isotope with a half-life of 10 minutes. After 1 half-life, only half of the original 4,000 nuclei remain. During each succeeding half-life, the number of remaining nuclei drops by half.
Okay. Human-made sources of radioactive material. They come out of the medical X-rays, nuclear weapons, consumer products, and nuclear power plants. Binding energy. The energy equivalent of the missing mass of a nucleus is called the binding energy. The greater the binding energy, the more the energy that must be supplied to break up the nucleus into its protons and neutrons. As you know, Einstein's theory has E equals mc squared. So matter is directly convertible into energy and energy into matter. Therefore, then binding energy then is exchanged by way of mass. A rendition of how a deuterium nucleus is split by a 2.2 MeV gamma ray. So the ray strikes the deuterium nucleus and breaks it up into a proton and a neutron. You will find that the isotope or the nuclei with the highest binding energy is iron Fe256. So lower than Fe256, the binding energy is smaller, and then greater than Fe256, the binding energy is also smaller. Therefore, you have the process or have the opportunity to use combining smaller particles to generate energy or breaking up larger particles to generate nuclear energy. So nuclear fission then, to split up most atoms will take more energy than can be released. However, in 1939, a process was discovered that caused a U-235 to become an unstable U-236 nucleus after absorbing a neutron. The unstable nucleus splits into the strontium-94 and the xenon-140, and a pair of neutrons and a number of gamma rays and heat. The important feature here is that you can start out with a U-235 nucleus as a source of radioactive material. Produce then from that U-236, and then you can go on to have a nuclear fission process. Here's a rendition here. You bombard the U-235 with neutrons, and you generate a U-236. And from that, it will spontaneously decay into strontium-94 and xenon-140 with the release of more neutrons. And then more neutrons then are available to impinge on other U-235, and therefore you can have a sustained fission process. Here's an illustration.
In the nuclear fission of uranium-235, a neutron collides with a uranium atom, causing it to fission into two smaller nuclei. On the average, 3 neutrons are emitted for every U-235 atom that divides.
Another illustration.
If the mass of U-235 is less than the critical mass, no chain reaction will result. Most of the neutrons will escape to the surroundings. If the mass is critical, most of the neutrons will be captured by other U-235 atoms, and an uncontrollable chain reaction will occur.
And so when you have an uncontrolled chain reaction, that will result in an atomic bomb. It is really a nuclear bomb, but the word atomic bomb has been labeled, so that's what we continue to call it. This is the way nuclear fusion occurs, the reaction that occurs in the sun. We have not learned how to have this process on Earth yet. But you see here a tritium atom, a deuterium hydrogen atom combines with a tritium hydrogen atom, generating a helium atom. So our sun makes helium from hydrogen with the liberation of 7.6 MeV of energy, a tremendous amount of energy. And these are processes that we are considering to be able to build a fusion reactor on Earth. Okay. Finally, there are 4 forces of nature. There's a strong force that happens inside of nucleus. There are weak forces, electromagnetic forces, and gravitational forces. That takes me to the end of this presentation.